Hello and welcome to this introductory video describing the Window to the Stars software. My name is Robert Izzard. I'm an astrophysicist at the University of Surrey, and I lead the Stars for Schools program, which uses Window to the Stars throughout. Stars for Schools is currently supported by STFC, the Science and Technology Funding Council, the Royal Society, and the Royal Astronomical Society, with help from many colleagues at other schools and universities, and in particular from Andy Britton of the Lady Eleanor Hollis School in Hampton. Today we will look at how to launch the Window to the Stars software, and I will explain some of its fundamental features. In future videos, I will talk about some of the more advanced features. But let's just start with the basics and see how we get on. So this is the desktop that you will see when you first load up your Raspberry Pi that is often provided, or you can buy and load up the Stars for Schools images. I'll talk in a different video about how to set up the Raspberry Pi, but for now, all you need to know is that when you run it, this is what you get. You can see various icons and hopefully my mouse pointer spinning around there. And this should remind you of any desktop from, say, a Windows machine, but this isn't running Windows, this is running Linux, which is free. The reason we use it is that we can then redistribute it as much as we want in any format that we like. So for this project, we put Window to the Stars on here, and it's all set up, ready to go. You click on this thing that looks like a globe at the top here. That's your web browser. And I've set this up in advance so that it points to the Stars for Schools website. But if you can't find it, it's at stars_for_schools.gitlab.io. If you just search on Google for Stars for Schools, you should be able to find it. The website has lots of information, both for the people doing the course at schools, their teachers, and for the mentors. And it has everything you need to get going. The opening page is, of course, a description of what the project is. And it says it's a project designed for 14 to 18-year-old students in school years roughly 10 to 13. We're working on expanding that, but for now, that's where we are. We use a Raspberry Pi computer to run the software, although you don't have to. We do, because that's much easier. This allays any problems that schools may have with security of loading software they don't know onto their Windows boxes. So we just avoid Windows, which is probably what everybody should do. We scroll up to the top, you can see there are various sections here. We have a news section. I click on that and it should load. Here it comes. There we go. So the latest news was just a few weeks ago. I will try to keep this up to date for you. You can spot stuff on here when it's new. I then have a menu where you can look at what happens when you want to take part. And we have an overview of instructions there for, say, schools or for people at universities, and especially for the mentors to the course. And I'll be meeting each of the mentors, probably virtually, but sometimes in person. So I really look forward to that. If you need help with the computing, you can click on that. This has mentions of exactly the Window to the Stars software we'll use today, but also the underlying stellar evolution code, which is Peter Eggleton's twin code. This is a chunk of hardcore number crunching code, but you don't have to worry about that, as you'll see today. You don't worry about the details, just worry that it works. There's a description here of how to install on a Raspberry Pi, or if you want to install it on Windows, you can install, for example, using VirtualBox or Docker. VirtualBox in particular is quite easy to use, and I'll show some examples of that in another video. I also give instructions for installing on Linux, because you can install on Linux very simply. We have a script that just installs on, say, Ubuntu Linux, and that works just fine on the Raspberry Pi as well. So that hopefully should make the process rather painless for you. We also have documentation. I'll show you the main document for the course today, but there's also the forms and the admin and all the boring stuff like that you need to fill in. This is particularly because when you're working on this project, you will need to fill in consent forms and things like that. So please do read through that and make sure these things are signed. There's a frequently asked questions list as well. That's for everything that doesn't fit in elsewhere. We have a page listing all the funding that goes into the project. Hopefully that will get enhanced as time goes on. At the moment, we're supported by the STFC Spark grant, which goes for the next few years. We also have money for some of the schools from the Royal Society. We've been very successful at achieving that. So thank you to both of them, and thank you also to the Royal Astronomical Society for advertising the project. The last two are the about. There's always an about section in every bit of software that shows you the people that have contributed to this, particularly to Stars to Schools in the past. It's a wonderful project, and if you want to get involved, please do get in touch. To get in touch, you click on the contact, and you'll see that there are several different ways to contact us. We have a Gmail address, which of course is the first place to go. I can read that, or Andy can read that. But you can also email each of us individually and directly at our places of work. And it's myself at the University of Surrey and Andy at the Lady Eleanor Hollis School. So that's the website. Hopefully that's useful for you. Next, we're going to look at what happens on the desktop. You can see on the desktop, other than the beautiful northern lights in the background, we have several icons here. I'll ignore the trash bin for now. That's where you put trash files and folders. We don't care about that too much at the moment. But let's look first at this Stars for Schools PDF document that's just sitting here. If I double click that, you see it loads immediately. That gives you your documentation for the Stars for School program. This is what we expect students to follow as they pass through from one stage to the next. And I'm not going to go through that in too much detail today because I'm focusing on the software. But you will need to go through this with your students, or if you are a student, you'll be quite used to doing this. The first section is all about stellar astrophysics and how we model stars. So that is how it's sort of an introduction into how stars work and what you should know about stars at this point, and what we'll try to teach throughout the course. The second part has projects you can do. We've got 4 or 5 projects here and a few suggestions for how you can do them, but you can make up your own projects as well. There's nothing that means that you have to do these. So please do feel free to do that, and please contribute them back because they will be great for new ideas for us as well. So that's the documentation. I'll leave that to you to read. It could take a little while. Now, the next thing on the desktop that you will want to consider is running Window to the Stars itself. There are 2 ways to do that. There's the basic mode, which I'll describe in a different video. That's the simpler mode, which I use on, for example, outreach evenings. We'll mostly want to use the advanced mode, and that's right. You are someone who is doing advanced stellar astrophysics. There's nothing better. You may as well go straight in and see what we can do with that. So let's run the advanced mode. I go to the icon and double click. You see pretty quickly we have a window appears. And this window, it's kind of like a web browser to the stars. Okay? It looks a little complicated at first, but let's go through it and see what each of these things means. So the first thing to see is that the window at the top, where you see my mouse walking across, the window at the top has a number of tabs, the options, evolve, HRD, and so on. These are the different parts of the software that you should use, and usually you should go logically from left to right. So we start by setting our options. What do I mean by options? Well, when we run a star, you have to choose some of its basic properties. The most obvious one is the mass of the star. What is the mass? A sun is 1 solar mass by definition, but many stars can be less massive than that or much more massive than that. Now, the twin code, as the name suggests, can actually run 2 stars, but we'll only run it in single star mode, so you don't have to worry too much about the binary star operation. Though to say, you can do it, and people have, so it's there to keep in mind. If I click on M1 here, this menu here, you can see I can choose the mass of the star. It defaults to 1 solar mass, but I could choose, for example, 10 solar masses or 100 solar masses, anything up to nearly 200. So let's stick to 1 solar mass today, just for our example. The second parameter you need to really care about, the second option, is the metallicity of the star. Now, you probably haven't studied metallicity. It is the content of the star that is not made of hydrogen or helium. And in a star like the Sun, this is only about 1.5%. It's a very small amount, 1 part in 100 roughly. So you think we might be able to ignore it, but it turns out that that content is very important, determining how big the star is, how opaque the material inside is, and then how long it lives. We'll stick with 2%, that's 0.02 for the sun. That's roughly what the sun is. We'll stick to that for today. Now, if I make this bigger, you can see there's a second set of tabs all sitting down here. These are the operation mode, initial conditions, initial abundances, and so on. These are all the very technical, sometimes, options that the star should consider. Some of them are technical in terms of how the code runs. Some of them are physical. To give you an idea of technical, you can set here the maximum number of what we call time steps. Time is not modeled in a linear way inside stars. We set it into time steps, that is long or short chunks of time that the star evolves for. When the star is changing rapidly, you need very short time steps, but you can have very long when the star is not doing so much that's interesting. So that you can set here, for example. However, you may also want to consider changing how the mass is lost from the star. And we have lots of prescriptions listed here with multipliers on them. So if the multiplier is 0, that's not applied. But if the multiplier is, say, 1, you will use the prescription from, for example, in this case, the Vasiliadis and Wood wind or something like that. You should probably leave these at the defaults, like most of the conditions in here. But just so you know, you can change them. And indeed, in the future, you will want to change them as part of your project. So have an explore in here, see what you can find for the different physics. You can put rotation, you can put orbital parameters for binaries. If you right-click on any of these, you get a drop-down menu, which allows you to very quickly choose one of these. For example, you want to change the nuclear network parameters. You can change them in here. Let's have a look. If you want to change the mesh in the star, because we discretize, we divide the star into shells, and what we call a mesh of shells. And you can change the number of them. The default is 199 shells, but you can set that to, 1,000 if you want, no problem. Other things in here you might want to change are, for example, the solver. This is how accurately you solve the equations. This means 1 part in 1 million is the error that we accept. You can make that smaller, you can make that larger, this kind of thing. So this is a very useful set of parameters you can change all the way through here. Now, what do you do when you've set your parameters? Well, that's when you go to the Evolve tab. At the moment, you see, there's some old stuff in here that I did previously, but let me click on Evolve to make a new 1 solar mass star. There we go. It's now running. You can see down here, the model number, this is the number of time steps, is going up, as is the time, which you see is here 9 times 10 to the 3 million years. So it's already up to the life of the sun. So it's getting there. Does that very fast. This is the time step that it's taking. This is the mass of the star, which is very nearly 1. I mean, you'll know that the sun has a very, very small wind, so that's taken into account. This is the luminosity in solar units. We have the effective temperature, that's the temperature at the surface of the star, and we also have the radius here. So these are, as a function of time, these change. But of course, this doesn't tell you much because this is changing all the time. You can't really read this. You could read all these colors that are in here. And this is the technical log that those of us might want to use that are trying to fix the code. And indeed, if you click follow log, you see this changes continuously and it keeps going back to the bottom so you can follow in real time. However, that's not very useful for people who want a quick way of understanding or a visual way of understanding what the star is doing. So we normally go straight to the HRD tab here. Now this is what we call a Hertzsprung-Russell diagram. It was invented more than 100 years ago. It shows the luminosity on the y-axis and the temperature on the x-axis. The luminosity is always in solar units, and then the logarithm of that is taken. And what that means is a value 0 is actually 10 to the power of 0, which is 1. So if you follow a horizontal line across from 0, that's 1 solar luminosity. The one that just appeared here is 10 to the 1. So this line here would be 10 solar luminosities. The 2 here would be 10 to the power 2. So that's 100 solar luminosities. It's what we call a log scale. And you see the star is very quickly becoming extremely bright. And that is why you need a log scale. Otherwise you would see nothing. Similarly, we plot the temperature also on a log scale, but the temperature varies much less. So that's a little easier to understand. What you can see is that the star starts down here, what looks like white or blue. That's because that's the color. I mean, the sun is reasonably white. It's actually peaks in the yellowy green, but it looks to us like it's white. And as the sun gets older, you go up here and it becomes redder. And you've probably seen red stars in the sky, and that's what the sun will become. There are many options for what you can do on here. You can zoom in on a region. For example, if I choose a region, I can left click and drag a square, rectangle, and you see it zooms in. How cool is that? I can go back to the old settings by using this arrow. It zooms back out. I can always reset everything by pressing the reset button. That resets the axes. Let's try that again. Let's just zoom in down here. Try again. You can see little wiggly bits. Isn't that nice? But I can go back, or I can reset. You can change the line colors. So you can plot anything here as the line color. For example, if I want to plot, what's a good thing here to plot? The log of the central temperature. There you go. That's now the log of the central temperature. Now, that means that it's cooler here and hotter here, but you can't know what it means. So what we do is we hit the color box button there. And now you can see what the central temperature, this is in Kelvin, by the way, and you can see it's logged again. So this is 10 to the 8 Kelvin is once the star is up here. So it gets extremely bright. Whereas down here, when the sun is born, it's around 10 to the 7.1. That's still 10 million degrees. That's a lot. But it's, you know, factor 10 less than when it's at the top of the giant branch here. We can also plot radii on here. If you click the radii button, these are lines of constant radius. So you see down here, if we zoom in down here again, let me turn this off and go back to stellar colors so it's obvious what we're doing. Down here, you can see these lines have numbers. The number is the actual radius. And you see this is nearly 1.97. So here is where you expect to be at 1 solar luminosity. And you see you hit 0. So you are at 1 solar luminosity when your star is 1 solar radius in size. That's a good thing. Remember, 0, because it's logarithmic, is 10 to the power 0, which is 1. So that's great. That works well, hopefully for you. And you can see here the star gets bigger as it ages up here. Now, how do we know that? Well, we started down here and we watched it go up here. You can see here it's 9 solar radii, up here it's 29, 93, and so on. So the star gets bigger as it goes up. How do we then know that it's aging up there? Well, you can click label with, and you can choose this one here, which is time in years. You see this number here now shows the time at any of these points. Now, you've probably seen standard form numbers before, such as this. This is 4.2 times 10 to the 5. What does that mean? Well, 10 to the 5, that's 5 zeros. So that's 423,000 years old at this point here. And then by the time you reach here, it's 7 times 10 to the 9. That's 7 billion years. So in that short time from here to here, which is extremely long, the star actually doesn't move very far. We can zoom in on this to see what's really going on. And what the star's doing, it very, very slowly reaches up here. This is a star like the sun. It's around 4 billion years old. But you knew that. So that just shows you the models work. Then you see it moves very little in this diagram. As the star gets older, it brightens a little bit, but not too much. Now let's reset and zoom back out. Now, interestingly, as you go up the giant branch, you see the number hardly changes. Just from 1.15, that's 11.5 billion years, up to 11.9 billion years. So in a very quick time, compared to all of down here in the bottom left, this star then moves up all the way up to become a very bright red supergiant. So it's a fascinating star. You can change a lot of the features on this diagram as well. You can change the label spacing. I usually have it set to auto, but if you need to change it manually, you can use one of these numbers here. You can have a play with those. You can also set a start label. Now, these are all the things that belong to the star at the beginning. I'm going to choose the mass here and do that as my start label. And you see now we have a 1 here. That's because we had a 1 solar mass star. Now, when you run multiple stars, as we'll show later, it's very useful to be able to choose which label you want. There are other options which you may or may not care about. The SHRD shows the spectroscopic version of the Hertzsprung-Russell diagram. That's almost the same, but it's slightly different on the y-axis at high luminosities. That's something that maybe I'll make a separate video about later, should we really care. Great. Now, most of the work you do will be in this tab. And so I'm going to leave this video here. And in the next video, we'll talk about the other tabs to see whether those are useful to you. Thanks for watching.